Okay, so I decided to offload this because it's a pretty long derivation, but I think it's good to see it. Um, we're looking at central force problems. A central force problem is really just where the force only is in the radial direction. And a good example of a central force is gravity. And so that's the example we're going to use. So we're going to imagine, in this case, we're going to talk about a satellite orbiting the Earth. This derivation is going to work for any orbiting object. It could be planets orbiting the sun or the moon orbiting the Earth, anything like that. But in this case, we're just going to pretend it's a satellite, it's orbiting the Earth. So as the satellite goes around, we're going to use polar coordinates because we're going to just look at the plane that the orbit lies in. And so we'll use our theta and radial components of unit vectors. What we're going to look at is we're going to say that this is our initial conditions. And so the initial distance is r naught, initial velocity is v naught. This is going to be probably the distance of closest approach, and you can see that the velocity vector is strictly perpendicular to the radius, the way it's measured, the r naught. So our force that we're talking about is the force of gravity, which we would say, in this case, we would write big G, the mass of the satellite, the mass of Earth, over r squared. And this is in the radial direction. I have to put the negative sign because you can see the radial direction points out. Gravity is going to point in. We're going to just actually rewrite this to get rid of some of the constants. Our acceleration of gravity would be big G, mass of the Earth, radius of the Earth squared. So we could sort of substitute in here, substitute this in, and rewrite this as minus mg re squared over r squared. So that's how we're going to write our force of gravity. Now let's go look at our two equations of motion that we have in this scenario. We're going to use polar coordinates, so we have a radial equation of motion and a tangential equation of motion, or theta. It's kind of the same thing. We've already talked about how we're writing the force in the radial direction. This is from the previous slide. We're just using our polar coordinate expressions for acceleration here. There is no force in the theta direction. The gravity's totally a central force. It's the whole point of this derivation. So these are our two equations of motion. And we're going to start here first, because we're going to come up with an important sort of result that we're going to use to simplify our equations. So I'm going to rewrite this using normal time derivative notation because I just think it's easier to take in. And we're going to get rid of the mass because we don't really need it. So I've just rewritten the acceleration term in the theta direction. And if we look at it, you kind of can see that we're using, it's almost like we're doing a derivative using the product rule. And in fact, if we sort of think on it long enough, we could say that what we're seeing is if we took the time derivative of r squared d theta dt, but then we divided that by 1 over r, we would get what we see over here. You know, this. And we're finding that this is equal to 0. What does that mean? If you take the time derivative of something and it's 0, it means it's a constant. So this material in the parentheses has to be a constant. We actually call these constants of motion when we figure this out. So r squared d theta dt has to be a constant. Another way we might write this is r squared omega. And we might also recognize that this is really angular momentum divided by mass. This shouldn't actually be a shock. We actually saw this idea in general physics that the gravitational force, as it acts on an object orbiting, acts in the radial direction, so it does not produce a torque. And when you have no torque and an object has angular momentum, that angular momentum remains constant. It's the basis of the conservation of angular momentum. Here we got at it mathematically, and we found that r squared omega was a constant. We call it a constant of the motion. It's because it's basically angular momentum. But in any case, we're going to use this. So if we just kind of redistribute our r here, these two things multiplied together actually gives us the velocity. So r times velocity is a constant. If we go back to our original problem, or actually go back to here, remember that we said initially r was r naught, v was v naught, and so we're going to use that as our sort of our constants. And what we can do is we can rearrange d theta dt can be written as r naught v naught over r squared. We're going to use this in the radial equation. So now we're going to have to turn the page. So remember, just as a reminder, our radial equation we had written as So doing that, we're going to just rewrite the acceleration term. So we've done a lot of rearranging, but essentially we have a second order differential equation which we could solve. If we did, the solution would be r as a function of t, but we don't want that. We actually want to know r as a function of theta because this would give us the path. So we have to do a change of variables. We want to get rid of time. So this is the change of variables we're going to do. We're going to say u is equal to 1 over r, just so we recognize it. Whenever we see r, that's going to be 1 over u. We also need to know how to write the derivative of r with respect to time, which would be, now it's the derivative of 1 over u with respect to time, which would give us minus 1 over u squared du dt equals minus 1 over u squared. Remember, we don't like time, we want to get rid of it. Du d theta, so we're going to use the chain rule, d theta dt. And remember from before, we already found a quantity to put in for d theta dt. Using our new change of variables, I can write this as u squared r naught v naught. So dr dt, we're going to be able to write as 1 over u, minus 1 over u squared, and then we're going to substitute in for d theta dt, that's u squared r naught v naught, and then du d theta. Simplifying it, this just becomes minus r naught v naught du d theta. So remember, all we're trying to do is change variables. So we want to rewrite things in terms of u and theta, which will essentially give us r and theta. To substitute in our equation of motion, we have to take the second derivative of r with respect to time and see how we would write it. So we use the results from our first derivative, take its derivative, and that was du d theta, and then we had this constant out front. Choose the chain rule. Finally, we have an expression for the second derivative of r with respect to time. we're going to substitute this in the radial equation. Remember, this was the second derivative of r with respect to time, but we just rewrote it. And then we had r d theta dt squared. Now, I have a little mixture here of u's and r's, so let's get rid of that. So it seems like kind of a mess. We can do some factoring. And we're going to even simplify it even more. And if we sort of isolate this that's in the brackets, so at this point, we have this differential equation. I'm going to go over to the next slide just so we have a little more room to work. And so we did a lot of crazy stuff, and I think it's kind of important to keep repeating, like, why did we do this? We were looking at a particular type of problem that's pretty common in physics, a central force problem. We used gravity as an example, but we could also use the electrostatic force, the force between charges. That also is a central force problem. And so these results are relevant. Early on, one of the things we saw was that there's this constant of motion. And so we can look at it from a mathematical point of view and a physics point of view. From a mathematical point of view, it allowed us to simplify our equations and to make some progress in solving them. From a physics point of view, we recognize that in this context, it represented the conservation of angular momentum, which was expected because of the fact that the force was central. It didn't exert a torque, therefore it will not change the angular momentum of the orbiting object. So we got to this point finally, and remember the reason we changed variables was that we want to eventually get an equation that's giving us the path of the orbiting object, and that's why we wanted it to depend on theta instead of depending on time. When you look at this, I want you to recognize, what is it? It's a non-homogeneous differential equation. It's second order because it's a second derivative. It's non-homogeneous because it's not equal to 0. Now, I might not be too impressed, but I want you to just look at this. What would it look like if it was homogeneous? And even then you might not recognize it, but what I want you to think about is how it has sort of the same form as the simple harmonic oscillator. Remember the simple harmonic oscillator, mass on a spring, had that second derivative and then was equal to some constant times the variable. This has the same form. And so the homogeneous solution of u of theta can be written as it's I sine theta plus b cosine theta. When we did the simple harmonic oscillator, we wrote it just in terms of one of those, but remember it had a phase constant. We could also have written it as a linear combination of sine and cosine. So that's a solution to the homogeneous equation, which we don't have. We have a non-homogeneous solution. The solution to the non-homogeneous equation is just you add that term and the way that we find A and B is we use the initial conditions. Initial conditions are that when theta was equal to 0, r was equal to r naught, or u is equal to 1 over r naught. V sub r is 0, v sub theta is v naught. So we're not going to go through all that. You've had enough derivation for the day. If you use those initial conditions, we find A is 0, and B can be written as 1 over r naught and so u of theta we can write as and that doesn't look all that impressive, but we have one last trick up our sleeve. If we introduce a quantity called the eccentricity and define it as r naught v naught squared over g re squared minus 1, then we can rewrite this we can actually rewrite the equation using the eccentricity. Okay, so we found this eccentricity. Again, I'm just going to write what we found it was equal to. So in the end, this equation of motion that we found Actually, the solutions are what we call conic sections. And which conic section they are depend on the value of E, which is the eccentricity. If the eccentricity is 0, then we have a circular orbit. If the eccentricity is equal to 1, we have a parabola. If E is less than 1, we have an ellipse. And if E is greater than 1, we have a hyperbola. They're called conic sections because they represent different cuts taken through a cone. And they describe different orbits, and you should sort of think about space and the fact that actually none of the orbits of the planets are circles, they're actually elliptical. But you can sometimes have, say, a comet or some other object coming close to, say, the Earth or the Sun, but it doesn't actually complete its orbit. It could get knocked into that orbit. It might have a parabolic orbit or a hyperbolic orbit, and it actually won't repeat. It'll just fly off into space, and that's possible too. In the end, what it really depends on is the actual value of the initial conditions. How fast was it initially going when it got pulled by gravity, and was gravity strong enough to actually keep it into an orbit that was fixed, like an elliptical orbit or a circular orbit, or is it going so fast that it can be deflected for a while but it's not actually going to be captured? So in a moment I'm going to look at an example problem of how we might use this. Okay, so we're going to use R over R naught is equal to 1 plus eccentricity, 1 plus eccentricity cosine theta. In this particular problem, we have the initial conditions for our satellite. It has initial R naught, 6,700 kilometers, initial velocity we're going to find, and we want the maximum radius of the orbit to be 13,400 kilometers. So this would represent theta equals 0, the initial conditions. The maximum is going to be over here that we're talking about. This is that other R. And theta over here is 180. And that's why I wrote that I'm going to use 180 here. So we're going to put some of these values in here. We're going to say our R that we're looking at is 13,400. Start at 6,700. 1 plus E over 1 minus E. And we find that our eccentricity of our orbit in this case is 0.33. We set that equal to R naught V naught squared over G R E squared minus 1. So we're going to be able to solve for V naught. I'm going to just do it over here. Eccentricity. And then our R naught was 6.7 times 10 to the 6. Now I have to do meters because I'm not dividing. Here I didn't need to convert since I was dividing kilometers by kilometers. Radius of the Earth is 6.37 times 10 to the 6 meters. And if I solve for this, I'll get V naught is equal to 8,886 meters per second. And so that was the velocity of our satellite at its closest approach. I know this derivation was a lot, but it's kind of an interesting technique. something for you. It's worthwhile looking at. You didn't have to do it. And the end result was something that we might be able to use to solve some central force problems.